the matter electromagnetically, and from that interaction people can detect that a photon has passed through it. Now, in general, in an experiment like LHC, photons will be created in all possible ways. For example, a pymeson can decay into 2 photons. So that is the source of photons. There are many other sources. I can draw, n number of Feynman diagrams probably, which produces, where n is very large, 2 photons. So there is no reason why this arbitrarily produced 2 photons will have a particular invariant mass. So this quantity is called the invariant mass of the, this is just a name, okay, this variable which is a kinematical variable. You do not need any theory. How these photons were produced, it doesn't matter. It is just a property of the motion of the photons, it is kinematics. And this must be equal to the mass of the Higgs boson. So there is no reason why the arbitrarily produced Higgs bosons will be having any particular invariant mass, and which is shown by the continuous distribution. That is, on the x-axis you have the invariant mass, and they have all kinds of things. But if the 2 photons come from a particle, their invariant mass must peak at the mass of the daughter, the mass of the mother particle. And since these guys are showing a little peak here, it tells you that it came from a particle whose mass is around, if you look into the plot, his mass is around 125 GeV or so. But that only tells you that it came from a particle. Okay? So a particle has been produced. And at that point of time there was no particle known to be of 125 GeV of mass, and therefore people thought that these guys must be coming from a new particle. But of course, in order to say that this is the Higgs boson, you have to do a lot more work. But before I do that, let me just go to a little bit of technicalities. Not really, because this is also understandable to anybody who is not a particle physicist but knows physics. And we see that this is a little distribution. Of course, there is a peak. This is the highest value of the invariant mass, which is 125. But why the hell this little bump here? Why it is not a sharp distribution which is having all the particles or the number of events peaked at 125 G. Now here the uncertainty principle comes into account. No big theory, no big quantum field theory, no big algebra. Just uncertainty principle helps us to understand this, and it says that here I will write down the time energy uncertainty, that is delta E is delta E times delta T is roughly equal to H cross, but delta E is the uncertainty in energy measurement, delta T is the uncertainty in time available for the measurement, and therefore we see from this that what is the uncertainty in measurement, uncertainty in time measurement? Well, if the particle lives for a finite interval of time, that is the uncertainty in the time measurement. So average lifetime, we can say, of the particle. And this immediately tells you that delta E cannot be 0 because the product has to be H cross, and delta E, if you like, is the uncertainty in its mass. You cannot say that it has mass m. Okay. So its mass or energy uncertainty is denoted normally by a width, okay, and that is denoted by gamma, and this is cross, and therefore you know that. So this is inversely proportional to the lifetime. So very nice. Therefore, if the lifetime is large, that means if the particle is stable, then this is negligible, the width. Then you will see a sharp peak. On the other hand, if a particle, because this h cross is a fantastically small number, so even if this particle has a fantastically small lifetime, gamma will still be large. That is, the invariant mass of the system will have a width. Now there is of course a scientific way for measuring the width. We are not going into all that. But what we are going into is that this little exercise in uncertainty principle tells you that why this is not a sharp peak but looks like a bump. Because it is coming from a particle having finite lifetime, and therefore, however small, and therefore it has a width. Now again, going back to your undergraduate physics, I just recall that although it is used by using quantum mechanics, probably you know from your little lab work in the undergraduate or postgraduate level, because you know that this is the exponential decay law. That is, if you have a number of unstable particles, its number reduces following this exponential decay law, and this gamma is the same gamma as here. And from this it is now clear that this gamma is a measure of the decay probability. If gamma is large, the exponential decay will be fast. Therefore, the population of the initial particles n0 will fall exponentially with time. For large gamma, the fall will be sharp, and therefore it has a larger decay probability. And if the decay probability is larger, lifetime will be smaller because it decays rapidly, and hence this inverse proportionality. Now this will be a very important variable in all our discussion, that a unstable particle has a width which can be measured experimentally. Now I come back to the lower figure, in fact, and what this shows, it shows that you collect in the previous plot, you collected photons, right? 2 photon systems. A lot of junk produced in that collision. You collected